So first, thank you, Boumediene, for the invitation. Thank you for everyone to be here. And okay, I'm going to present this work. It's the first time that I present this work. So every comment, negative or positive, is welcome. Okay. So it's a joint work with Reza and Anastasis that are from McMaster University. And in particular, I would like to give the credit to Reza, to the numerical part that I'm going to present. And the other two co-authors are from King's College, and is John Armstrong and Luca Galimberti. You can find the paper at this link together with, and also the code will be available at this GitHub link. And the name is Low-Dimensional Approximation for the Conditional Law of Volterra Processes, a non-positive curvative approach. Okay, so I start by presenting basically our problem, so the problem that we take into account, and how we provide a solution to this problem. So the research question is the following. So we would like basically to efficiently predict via a machine learning model. So we would like to propose a machine learning architecture, the conditional distribution of a non-Markovian Volterra processes, and the condition on the realized path. So if you look at this problem, there are basically two main issues that arise. And the first one is the measure valued map is infinitely dimensional, and so you suffer from these problems suffer from the so-called curse of dimensionality. And the second issue is that most spaces of probability measures, so you can think, for instance, the Wasserstein space, okay, do not have any smooth or linear structure, and therefore is, let's say, difficult to leverage on some deep learning models to approximate these conditional distributions. So here you can find some, obviously we are not the first that we try to solve this problem, and here you can find some references specifically on machine learning models that try to learn the conditional distribution on a historical path. Okay. So how we answer to this question, so how we try to answer to this question is via these 2 points. So regarding the first, actually regarding this second problem, okay, so we propose this projection. So we propose a projection for this conditional distribution into a smooth Riemannian manifold. What is this manifold? Is this manifold of the non-singular Gaussian measure of a given dimension D. And we keep this space with a new Riemannian metric. And the main point that of this new Riemannian metric is that it will have a non-positive curvative geometry when D is greater or equal than 2. So we found, I'm not claiming that is an exhaustive literature, but we found some results in literature that try to, let's say, to use this geometry in this space, but it turns out that some of this geometry is a non-positive curvature only for D equal to 1. Okay, so we come up with this new geometry that I'm going to explain. And so once that we use this projection for this conditional distribution, so basically what we obtain is a long memory dynamical system in the sense that I'm going to present. And the second point is, okay, so we leverage on this previous work of Anastasis, and we approximate this dynamical system by a dynamic version of the model that Anastasis proposed in a previous paper. And the nice thing is that we are able to prove also quantitative universal approximation theorem on this model that we are going to propose. So one observation is that if you're going to read the paper, all the paper, okay, basically focus on this statistical manifold, so on the statistical manifold of the non-singular Gaussian measure, but all the results basically can be adapted to dynamical system on any non-positive curvature Riemannian manifold. Okay, so this is a remark that I'm going to say. And for the main reference for this model is this one by Anastasis. Okay, so let's go to the problem setting, let's say. So I'm going to present the setting that we are going to present. So we fix T, and we take into account a stochastic process, X, defined in this way. And this process evolves according to these equations, okay? In this equation, we have that this W is a Gaussian white noise that is defined on some probability space, and S is a symmetric valued stochastic process that it is independent both on the Gaussian white noise and on the starting point. So the title of the talk is about Volterra processes. So now let's define what is, okay, for us a Volterra process. So is a process that, okay, it is defined for a non-singular diffusions, okay? It is a discrete time stochastic process where the previous two quantities, so basically this drift and the diffusion, have a particular forms. So in particular, they are defined in terms of this kernel, okay? So the drift is defined in the following way, and the diffusion is defined in this way. So here we have that this exp denotes the matrix exponential. We have some constraint on the parameters that define this evolution. So basically both mu and sigma are Lipschitz, when with L I denote the best Lipschitz constant, okay? So this kappa is a Volterra kernel. What is a Volterra kernel? Is a real valued function that in our case we were able to provide a theoretical result if we assume either an exponential decay for the kernel or a polynomial decay. Okay, so this is our basic assumption that we are going to work. And again, this sim is the space of the symmetric D by D dimensional matrix. Okay. So, okay, this is the main weakness, let's say, of the work, in the sense that we are not, so far, we were not able to relax these assumptions. So, again, we admit that this is, let's say, a strong assumption, okay? And this assumption is required for the existence of the barycenter map. So we will see that when we will do this projection, we are going to leverage to some existing result by Sturm. And basically, we need to impose this uniformly bounded assumption on the stochastic factor. So remember that the stochastic factor is the S, okay, that enters in this in the diffusion. Okay. Okay. One example that fits into this framework, okay, can be this the discretization of stochastic delay differential equations. So if you discretize a stochastic delay differential equation, you can basically you can see that this discretization fits the framework that we are going to present. Okay, so if you have any, I don't know, later on any hint on this or on how to relax this assumption, they are very welcome. So, as I said, we are going to project, let's say, our conditional probability distribution on the manifold of the non-singular Gaussian distribution, d by d, d-dimensional, okay? And basically, on this manifold, we are going, okay, to propose a new Fisher geometry. So how? So we construct this geometry in this way. So in particular, it turns out that it will be a perturbation of the Fisher matrix, and where the main difference in these definitions. So, but let's go with some notation. So if this is the space of the d by d non-singular Gaussian measure, okay, where m is the mean, so it's a vector in Rd, and the sigma is a positive definite matrix that it is symmetric, d by d. So if you introduce this map, so you take a point in this space, okay, and you define this mapping, what you can see is that this space, okay, can be isomorphic to an open set, okay. This open set is a subset of Rm with the m that it is defined by this dimension, that is basically d plus the element that characterizes basically the covariance matrix. So in particular, this ND, okay, with thanks to this map, can be define basically a differential manifold of dimension m, with m that it is defined in this way, and this ND with this phi is a global chart. So what we did is to perturb this Fisher matrix in this way. So instead of taking this sigma ij, so for the first component here, we take the delta ij, where this delta denotes the standard Riemannian metric on Rd. So this is the main difference with respect to the Fisher metric. What is the advantage, okay, of doing this is the following. So the advantage is that so this is the ND with the metric that we propose, so that is defined in this equation 2. And we are able to achieve these characteristics. So it is complete. So it is it has a non-positive curvature. So we are able to use these to construct these barycenters, basically. Okay. So we derived also a closed form distance, and it has isometric copies. So we, in the literature, we were able, okay, it is up to our knowledge to find our other metrics, geometry, okay, on this space with these characteristics. So again, so if you know some other geometry that can fill in this framework that we are not aware of, so any suggestion is welcome, okay. Yeah. It's only a characteristics that actually we do not use in the end, but just to describe all the characteristics of this geometry, basically. But the important stuff is this one, so that we are this non-positive curvature space for D that is also greater or equal than 2, and not only for D equal to 1. Okay. So now the next step is to construct these projections, so these random projections. And I'm not going, obviously, to go over all these details. The main takeaway of this slide is the following, so that basically all the argument that we are going to present, okay, hinge on this, on the fact that the regular conditional distributions function that send this point to this conditional probability, okay, belongs to ND, okay, and so this is like all the steps that you need, okay, in order to prove that this conditional distribution belongs in ND. That the map, okay, that send this point to this conditional distribution, okay, the image belongs to ND, okay. So this is the only, I'm not going obviously to go into the details, but if you are interested, then the slide will be available so you can have a look. Okay, so as I said before, we basically based our construction, this projection, on this work by Sturm. And the main proposition that we used is the following. So basically I'm going to read the statement. So we have this ND that is a global non-positive curvature space. So you fix a y in this space, And then for each Q, that this is the set of probability measured with the finite first moment, okay? There exists a unique point Z that minimizes this functional. And this point, basically, it is independent of the Y that you select at the beginning, and it is called barycenter. So remember this, only this notation beta of Q, because I'm going to use this notation later on in the talk, okay? And this beta of Q, okay, basically minimize is the argmin of this quantity. So here you find basically the main reference that we use in the geometric part of the paper. So this is the theorem basically that we derived based on this result by Sturm. So again, in the end we are going to provide an approximation, a universal approximation theorem. So what we need is to work on compact set. So in particular, it's for this reason that now this compact set came out of the blue, okay? So we fix T, we fix a compact set. Now, the equation 1 is the dynamics for the Volterra process, okay? And we need this assumption, this is the strong assumption on the boundness on the stochastic factor. So this map that takes this basically path from 0 to T, and remember that this is the barycenter, okay, is well defined and Lipschitz. So this is an informal, let's say, definition. Why? Because in some sense we need to, so basically if this S is deterministic, so it is like the distribution is Gaussian, so we need in some sense to randomize this measure. So informally, we plug the randomness of the stochastic factor basically here, okay? So, and the Lipschitz constant of this function depend only on T, okay? And on the constant R that basically define the boundness of our stochastic factor. So is it precisely in this point that we need the strong assumption, the boundness of a stochastic factor. Okay, so what we take into account, okay, is this, we have this theorem before providing the universal approximation result. So again, we work under the assumption, the boundness of the stochastic factor, okay. So we work again under the assumption that the Volterra kernel kappa either satisfy an exponential decay or a polynomial decay, okay. Now we fix a compact because in the end we are going to provide an universal approximation result, and for each compact we prove that there exists a constant such that for every pair of integers this H defines the so-called memory, okay, of our process, and T, okay, that satisfy this inequality. We have this, there exists a Lipschitz function, okay, from Rd to this space of Gaussian non-singular measure, okay, with this new matrix that we constructed before, that satisfy this bound, okay, and this bound basically it will be used in our universal approximation result. And this property is very similar to this fading memory property that one has in the reservoir computing. And okay, here there is this work by Liudmila and Juan Pablo. Okay, now some assumption in order before to state this universal approximation result is on the regularity of the input and output manifold. So we take into account this C infinity Riemannian manifold, okay, of dimension capital D and small d, and we assume that we have this assumption that is that they are geodesically complete, simply connected, and the sectional curvature is bounded, okay, in minus kappa 0 for some kappa greater than 0. And for instance, you can think about to this example. So the Euclidean space satisfies this assumption with kappa equal to 0, and this space of sorry, this space of a non-singular d by d Gaussian measure satisfy the previous assumption with the kappa equal to -1 alpha. Okay, so this is the assumption that we have on the input and output manifold for our approximation result. Okay, I put only the two pictures in order to present. Obviously, Anastasis did this picture in order to present the two theorems. So basically, if you read the work, it is divided in two main steps. So we have a static result and we have a dynamic result. So basically, once that you have the static result, the approximation in the static case, we have a trick in order to, by using an hypernetwork, in order to extend this static result, okay, in a dynamic setting. So you apply this approximation result, okay, at every point in time. So the idea is very simple, let's say. So basically, this is the geometric deep neural network model that Anastasis developed actually in his work. Okay, how it works? So it takes in input this point. So this is again the manifold in input, and you can interpret this okay this input, okay, as a sequential point from -m up to 0. So this is in the space in input n, and we have this process in 3 steps. So we have an encoding, a transformation, and a decoding phase. So actually, this should be okay. This one, okay. First, the colors are not right, but basically we have first an encoding phase, okay, in which the input, okay, in this space n. Remember that h is the memory of the process that we have in input, okay. So it linearized this input along some geodesic that emanates basically from a set of reference points. Then we transform this linearized input at this point with this ReLU neural network. And then we have a decoding phase that maps this in this f at, that this f is the neural network that approximates our function, okay, on the output manifold. So this is the main idea. Okay, so this is the definition. Now we would like to move on a dynamical setting. So as I said before, basically we are going, the main trick is to basically use an hypernetwork in order, okay, to evolve, so let's say, the parameters of our static network at each point in time. So we take this map, okay, and we define this hypergeometric network if there exists some parameters that define basically the architecture of the network. And an hypernetwork that is a simple ReLU, neural network with a ReLU activation function, okay, a multi-layer perceptron neural network with a ReLU activation function, an initial parameter z, and we have this linear readout that can, okay, that define the evolution of the parameters, basically in this way. Okay, and I will call this hypergeometric network via this set of parameters that characterize basically the architecture of the network. Okay, so this is the other picture. So the main difference with respect to the static basically setting is the presence of this hypernetwork. Why? Because this hypernetwork is going to update, okay, the multi-layer perceptron parameters, okay, at each point in time. So basically the encoding phase and the decoding phase is the same, but we have this hypernetwork that allows us basically to encode, okay, to update the parameters from time t to time t plus 1. Okay. So in order to define a universal approximation result, we have to define what kind of function we are able, let's say, to approximate with our neural network. and we are able to approximate this type of function. So the so-called causal maps of a finite virtual memory between advar manifold. So this is the class of function that we are able to approximate with this neural network. So again, we take a map F. So since we have to provide a universal approximation result, this capital K is a compact, okay? And this function F is a causal map with a virtual memory R if it satisfies the following, let's say, technical conditions, okay? So basically we have a compression lever epsilon, okay? And at each time horizon capital T, we are able to find this capital, this integer h. Remember that h plays the role of the memory of our network that satisfies this basically inequality. Okay, so this is the map that we are able to approximate, and this is the theorem actually, okay, that defined these universal approximations. Okay, so I'm not going to go into all the details, okay, but the main point is that we have these basically estimate, okay, on this function f is this function f is the previous causal map of virtual memory, okay, and this capital F, okay, is this hypergeometric network that is able to approximate our function f, okay, with an error that is less than epsilon. So I didn't put the explicit form for the parameters, but in the paper you can find the table with the precise basically dependence on the parameters of the layers and the hidden layers and hidden neurons of the architectures. Okay, so 2 minutes only. Okay, I just to give credit to Reza that work a lot on the numerical part. So we have a simple example in the paper. So basically we take into account these ID Bernoulli variables, okay, that takes values in 0, 1 with equal probability, and we have to define, okay, these random factors, the stochastic factor, and so we fix this randomness parameter lambda and define this random matrix. So one can write down these dynamics, okay, for the process X. And basically, okay, the process is very simple, okay, and one can can see that this random variable that define was used to define this barycenter, okay, it is defined in the following way. So we leverage on this proposition by Sturm, and we have that the barycenter, okay, is given by this Gaussian variable. Okay, we use basically this result. So here is how we train the model. So basically this is a copy and paste of one page of the article that I'm not going to explain in detail because of the time. But this is the result that I would like only to show. So in particular, we have that in blue, we have this is the static version basically of this model. So at each point in time, we approximate the series. So it's the best basically that you can do because you're not forecasting a dynamic way, let's say your process. So and you can see that both. Okay, this is the one step. So basically, we train the model, then you predict from t to t+1, from t+1, t+2, and so on and so forth. In green, instead, we have this. We do this h-step forecast ahead, for instance. Okay, and you can see that basically all the 3 models align well. So at least in this very simple example, not claiming that it works. For every example, but we're pretty happy about the performance of the result in this example. And I stop here. Thank you.